Okay guys, so here's problem number 4. We've got a 600 Newton force applied downward on the handle of a lawnmower. The handle of the lawnmower makes a 50-degree angle with a horizontal. We know the mass of that lawnmower is 10 kilograms, and it accelerates at 20 meters per second square. We want to know how much frictional force acts on the lawnmower, its normal force, and the coefficient of friction. So let's go to another slide, and let's figure out how we would go about doing this. First of all, it's always a good idea to draw out a picture. So if this were our lawnmower, here's our handle. We're applying a force on the handle of 600 newtons, and that's down the handle. And that handle makes a 50-degree angle with a horizontal. That's supposed to be 50. The mass of the lawnmower is 10 kilograms. And we're accelerating this thing at 20 meters per second square. We want to know the frictional force, a normal force, and the coefficient of friction. So the first thing we're going to do is figure out the weight of this lawnmower. Remember that weight equals mass times gravity. So the weight would be 10 kilograms times 9.8 newtons. The weight of our lawnmower, therefore, is 98 newtons. Now, the other thing that we need to think about is the net force. We know that net force equals ma. So in this problem, m times a. So 10 kilograms times 20 meters per second square, we seem to have a net force of 200 newtons acting in that direction. Now, first thing we're going to do from here is we're going to draw down a vertical on our lawnmower, and we're going to break that 600 newtons of applied force into components. So we'll draw this down like so. Now what we want to know is, of that 600 newtons, how much of that is horizontal and how much of it is vertical. So to find the horizontal part, we're going to use cosine. And we'll say the cosine of 50 equals our horizontal over our total, over our hypotenuse, 600. So when we do that, 50 cosine times 600, we end up with about 386 newtons. To find our vertical, we'll do the sine. And we'll say the sine of 50, and that's a 50, trust me on that. The sine of 50 equals our vertical over 600. All right, so sine of 50 times 600. Our vertical force is 460 newtons. I'm going to write that here. And that vertical force is against the ground. Here's the thing. We seem to have a net force of 200 newtons side to side. But we're applying a horizontal force of 386 newtons side to side. Which means the difference between these two forces, 186 newtons, seems to be disappearing somewhere. That's friction. The frictional force in this problem is 186 newtons going to the left. Now to get those other two things, the frictional force and the normal force, remember the normal force is the force that's pushing the two surfaces together. So in this problem, the forces that are pushing the lawnmower against the ground are, number one, the weight of the lawnmower, and number two, the force that we're pushing down on the handle. So if we add 460 and 98, that'll give us the force pushing the lawnmower to the ground. So 460 plus 98, we have a total normal force of 558 newtons. Now we want to solve for the coefficient of friction. So we'll use what I call the fun equation. Solve that out for mu. in this problem, the frictional force is 186 newtons. The normal force is 558. Cancel out the newtons. Coefficients don't have units. We'll have 186 divided by 558. And we end up with a coefficient of friction here of a third. So mu equals 0.333. Hope that helps. All right, so here's problem 5. In problem 5, we've got a 600 Newton box sliding down a 40-degree incline. It's got a constant acceleration, uniform acceleration of 3 meters per second square. We want to know the components of the box's weight. We want to know the net force, the frictional force, and the coefficient of friction. So let's go to another slide. Draw this out first of all, and then we'll go from there. So again, a good picture is key. So here's our incline. And on this incline we have a box. The box has a weight of 600 newtons. It's always a good idea to find the mass. Remember that weight equals mass times gravity. So if we divide 600 by 9.8, we get a mass of 61.2 kilograms. We also know in this problem that our angle is 40. And we know that it accelerates down the incline at 3 meters per second squared. First thing you want to do in a problem like this is draw from the center of your box, draw a line straight down. I'm going to try that again. My board's a little off here. So let's draw an incline. Draw in our box. Draw in a line that represents the weight, straight down. We want to draw in our components. One component parallel to the surface of the box. One component perpendicular to the surface of the plane. We want to make that into a parallelogram. Now what you have to realize to work this problem, if the angle of our incline is 40, the two triangles inside our parallelogram are similar to that triangle. If this angle is 40, this angle is also 40, and this angle is also 40. We know the line going down here represents the weight of the box. The weight of the box in this problem is 600 newtons. We need to find, first question asks us, what are the components of the box's weight parallel and perpendicular to the plane? This up here represents the parallel component. This over here represents the perpendicular component. So to find that parallel component, we can use the sine. And we can say the sine of 40, which this angle right here is 40 degrees, is equal to the parallel component over our hypotenuse, which is 600. And for the perpendicular component, cosine of 40 equals perpendicular component over 600. So if we do the math on that, sine of 40 times 600, we get a parallel component of 386 newtons. And if we do the math on the perpendicular one, cosine of 40 times 600, we end up with 460 newtons for that. That's our answer to the first question. Second question says, what net force acts down the incline? Well, for net force, we're going to use F net equals ma. We know the mass and we know the acceleration. So to get the net force, we're just going to go mass times acceleration. So 61.2 kilograms times 3 meters per second square We end up with three significant digits, 184 newtons. That's down the incline. Now the other thing we've got to do in the third part of the problem is find the frictional force. And here's what we know. We know we have a parallel component of 386 newtons that's pushing the box this way. But we only have 184 newtons of net force. So there's 202 newtons that seem to be disappearing. And the way I get that 202 is 386 minus 184. Those seem to go away. Something's canceling out part of this and only leaving this 184 behind. So that 202 represents friction. We have 202 newtons of friction acting up the plane, 386 newtons of parallel force acting down the plane. Those add together to be the 184 newtons of net force. And the last part of the problem is to find the coefficient of friction. And I want to make some space to do that over here. To find the coefficient of friction, we'll use what I call the fun equation. We want to solve for mu. We just figured out that our frictional force was 202 newtons. And remember that the normal force is the amount of force pushing the two surfaces together. Well, in these kinds of problems, the force pushing our two surfaces together is the perpendicular component of our weight. 460 newtons. That's pushing the box into the plane. So if we put 460 there in for the normal force, and we go 202 divided by 460, we end up with a coefficient of friction, mu equal to 0.439. All right, on to the next problem, on to number 5. All right, guys, the last one of these problems we're going to look at today is this one. A book is given a single push and slides freely across a tabletop. If the coefficient of friction between the table and the book is 0.30, what is the magnitude of the book's acceleration? At first look, it doesn't look like you have enough information to work this problem. But here's the situation. Here's our book. Here's our table. And all we know right now is that mu equals 0.30. Remember, once I give that book a push, I'm not applying any force after that. So the only force acting on this book after I let it go is friction. Friction's acting this way. It's accelerating the book. It's slowing it down in this case. But the key thing is here that once my hand leaves the book, the only force acting on the book is friction. Therefore, the frictional force is equal to the net force. Let's do a little work on this. We know that frictional force is equal to mu times N. We know that net force is equal to M times A. This problem's taking place on a flat tabletop. Remember that the normal force is the force that pushes two surfaces together. On a flat tabletop, the force pushing the book into the table is the book's weight. So we're going to make another substitution. For N, we're going to substitute weight, which is mass times gravity. That's still equal to net force, MA. So what I hope you see is that the two masses cancel out. So that what we have in terms of an equation is that the coefficient of friction times G, 9.8, is equal to our acceleration. So we plug in what we know. We know the coefficient is 0.30. We know the acceleration due to gravity is 9.8. We solve out for A. So 0.30 times 9.8 gives us an acceleration of 2.94. And that's meters per second squared. Hope that helps. All right, guys, we're going to go ahead and look at one more problem. In this one, we have a 20-kilogram bucket hanging from a rope, and we want to know what net force must be applied to the rope to accelerate the bucket at 2 meters per second square. And then we also want to know the total amount of force that needs to be applied to do that. So let's go and draw a picture. Here's our rope, our handle, and our bucket. And we know the mass of the bucket is 20 kilograms. That's mass. We know the bucket is accelerating at 2 meters per second squared. And what we want to know first of all is the net force that needs to be applied. Well, we know that F net equals MA. So we're going to go 20 kilograms times 2 meters per second squared. So the net force is going to be 40, and a kilogram times a meter per second squared is a newton. So we're going to apply 40 newtons in the upward direction. That's the answer to the first part. Second part, a little tougher for people to understand. Just to hold this bucket in place, to keep it from accelerating, we have to apply force equal to the weight of this object. Well, we know that weight equals mg. So in this problem, 20 kilograms times g, 9.8 meters per second squared is going to give us weight. Well, if we go 20 times 9.8, we end up with 196 newtons. Just to hold the bucket in place, we have to apply 196 newtons of force. To make it accelerate at 2 meters per second squared, we have to apply an additional 40 newtons. So the total force that we have to use to make this bucket accelerate upward is the 196 to cancel out the weight, plus the 40 net force to make the acceleration happen. So we end up with a total force in this problem of 236 newtons of total force. And again, that's the weight plus the net force. All right, hope that helps.